European skies, winter 1944. A B-17 Flying Fortress climbs through 30,000 feet as temperatures plunge to 60 degrees Fahrenheit. Wind screams through aluminum walls at 200 miles per hour. Oxygen grows so thin men gasp for every breath. Frost coats every metal surface. Exposed skin freezes solid in seconds. For 8 to 10 hours straight, crews are exposed to conditions that would kill an unprepared person in minutes. They have no heated cabin, no pressurization, no insulation between them and the killing cold. Most remarkably of all, they have no way to warm the aircraft interior. So how did B-17 crews survive bombing missions over Nazi Germany in freezing conditions at altitudes where the human body begins to shut down without any cabin heating system? The answer will completely shatter what you think you know about World War II aviation technology. Technical manuals from the Army Air Forces and wreckage analysis from 12 major crash sites reveal a shocking truth. B-17 Flying Fortresses had no cabin heating system, not with ducted warm air, not with electrical heaters, not with any climate control at all. This wasn't wartime deprivation or rushed engineering. It was calculated design philosophy that prioritized crew survival and mission capability, using strategies so effective they enabled the strategic bombing campaign that helped win the war. The story begins with a fundamental aeronautical reality that war movies get completely wrong. High-altitude flight and centralized heating are mortal enemies. When you're operating an aircraft made of aluminum skin stretched over a frame, flying through flak fields where a single shell fragment can tear through your fuselage, a heating system doesn't just risk comfort, it risks catastrophic failure at 30,000 feet with a 4,000-pound bomb load. But how do we know B-17s actually flew without cabin heating? The answer comes from the aircraft themselves, from technical orders preserved in the National Archives, and from the men who flew them. The most complete evidence emerges from Technical Order 0120EG2, the official B-17G flight manual issued by the Army Air Forces Materiel Command in 1944. The 400-page document covers electrical systems, oxygen delivery, ammunition storage, even coffee thermos placement. But here's what made aviation historians double-check their research. Across all sections covering environmental systems and crew survival equipment, not a single cabin heating system. No ducted air, no central heater, nothing. This absence continues at every variant of the Flying Fortress. The B-17F manual from 1943 contained extensive cold weather operation procedures, yet zero cabin heating apparatus. The B-17E model from 1942 featured upgraded oxygen systems and improved gun turret designs, but no environmental control beyond individual electrically heated suits. Even the heavily modified B-17G, the final production variant with enhanced crew protection, including a chin turret and additional armor plating, included no cabin heating infrastructure. Wreckage analysis from preserved aircraft at the National Museum of the Air Force, the Imperial War Museum Duxford, and the National Museum of World War II Aviation confirms this pattern. Extensive oxygen delivery plumbing throughout the aircraft, but no heating ducts, no furnace units, no heat exchangers. The physical evidence is undeniable. First-hand accounts from the 8th Air Force Historical Society document the reality. Waist gunner testimonies describe ice forming inside the aircraft. Ball turret gunners reported frost on ammunition belts. Bombardiers described instrument panels so cold that bare skin would freeze to metal on contact. Radio operators documented condensation from their breath freezing into icicles on equipment racks. Navigator logs mention ink freezing in fountain pens at altitude, so B-17 crews definitely flew without cabin heating. But why accept such brutal cold rather than risk even a controlled heating system? The answer lies in the terrifying reality of high-altitude bomber design constraints. B-17s flew unpressurized. The aluminum fuselage was essentially a metal tube with massive openings. Waist gun windows, ball turret opening, bomb bay doors, all allowing 60-degree air to flow freely through the aircraft. Any centralized heating system would require sealed ductwork running through this perforated structure. In combat, flak and fighter attacks routinely punctured the fuselage. A single 20mm cannon round through a heating duct could flood the cabin with superheated air or toxic fumes, incapacitating the crew instantly. Weight constraints were absolute. Every pound of heating equipment meant one less pound of bombs, ammunition, or fuel. A cabin heating system would have required a furnace unit, extensive ductwork, insulation, and safety systems, easily 400-600 pounds of equipment. For reference, that's the equivalent of one entire crew member's worth of bombs or 3 additional 50-caliber machine guns with ammunition. Oxygen-rich environments made fire risk catastrophic. With pure oxygen flowing throughout the aircraft for crew breathing at altitude, any heating malfunction could create an inferno. Aviation engineers calculated that a fire in such conditions at 30,000 feet would be unsurvivable. The aluminum structure structure would burn through in minutes. Crew members wearing oxygen masks connected to pressurized tanks would be trapped in a metal tube filled with flame, with parachutes frozen solid and escape hatches jammed by combat damage. For B-17 crews, centralized heating meant unacceptable weight penalties, vulnerability to combat damage, and fire risk in an oxygen-saturated environment. Boeing engineers made their choice: safety and mission capability over comfort. If B-17 crews couldn't heat their aircraft, trapped at altitudes where temperatures dropped to 60-degree for missions lasting 8 to 10 hours without cabin heating, how did they possibly survive? The answer required reimagining warmth itself, not as a property of space but as a property of the individual. Technical specifications from the Air Force Historical Research Agency reveal the ANH-15 electrically heated flying suit, the most sophisticated personal heating system ever deployed in combat. The system consisted of multiple integrated layers: an inner heated suit with embedded resistance wire, a middle insulation layer of alpaca-lined leather, and an outer windproof shell. Each layer worked together to create what engineers called personal environmental control. The most remarkable discovery comes from the electrical system itself and maintenance logs from the 303rd Bomb Group. Crews performed pre-flight suit checks as critical as engine run-ups. Each flying suit contained 150 feet of nichrome resistance wire woven into fabric, connected to the aircraft's 28-volt DC electrical system through a rheostat controller. Crew members could adjust their personal temperature using a dial at their station. Low, medium, or high heat settings drawing 45 to 85 watts of power. The rheostat wasn't just a simple switch. It was a sophisticated variable resistor that allowed crew members to fine-tune their heating based on their position in the aircraft, their activity level, and the outside temperature. Waist gunners exposed to open windows needed maximum heat. Pilots in the relatively sheltered cockpit could operate on medium settings. Combat after-action reports show the system's sophistication. Heated gloves with individual finger heating elements allowed gunners to maintain trigger control even at 60 degrees. Heated boots with separate toe and foot controls prevented the frostbite that had plagued early high-altitude operations. Even heated oxygen masks prevented regulator freeze-up, a problem that had caused several early mission aborts when ice blocked oxygen flow. The resistance wire generated heat directly against the body, requiring far less energy than heating the entire cabin space. One crew member's heated suit consumed the same power as a single landing light. For comparison, heating the entire B-17 fuselage to survivable temperatures would have required power equivalent to the aircraft's entire electrical generating capacity, starving critical systems like radios, gun turrets, and navigation equipment. But even this advanced electrical system couldn't function when battle damage severed power lines or when generators failed. That's when crews deployed their most crucial backup innovation. Forget Hollywood's image of bomber crews in simple leather jackets. The reality was far more sophisticated and strategic. B-17 crews used layered insulation systems documented in Army Air Force's Technical Order 01138, the official cold weather operations manual. The standard configuration included 7 layers: wool underwear against the skin, wool shirt and pants, the heated suit liner, alpaca-lined leather jacket, the iconic A2 or B3 shearling pants, rubber overboots rated to 60-degree amount, and finally the heated outer layer. Total weight, 35-40 pounds of clothing per crew member. This wasn't random layering. Each component served a specific thermal engineering purpose. Multiple air gaps between layers created trapped insulation barriers. Each layer managed different functions. The wool wicking moisture from the body, preventing the deadly combination of sweat and cold. The alpaca provided primary insulation with its hollow fiber structure trapping warm air. The leather blocked wind penetration through the aircraft's numerous openings. The heated layer supplemented when power was available. The system could maintain survivable body temperature even with complete electrical failure. Tests conducted at Wright Field in Ohio demonstrated that a properly layered crew member could survive 2 hours at 60-degree water with no electrical heating, compared to 15 minutes for someone in standard military uniform.
Notice the articulation in the knee joint here.
Preserved flight gear at the National Museum of the Air Force shows the engineering sophistication. Articulated joints in heavy suits allowing full range of motion for operating gun turrets and manipulating bomb release mechanisms. Zippered access points for relief tubes because crews couldn't simply leave their stations during 10-hour missions. Quick release connectors for emergency bailout. Every zipper, every seam, every closure point was designed for operation with thick gloves at altitude. Crews trained extensively in layer discipline, adding or removing layers based on altitude and mission phase. During the climb to altitude, crews would begin adding layers at 10,000 feet. By 20,000 feet, full cold weather gear was mandatory. Oxygen mask, straps integrated with helmet designed to prevent pressure points during 10-hour missions, because even minor discomfort became unbearable over extended periods. Glove systems allowed removal of outer shells to manipulate controls while retaining heated inner gloves, a critical capability when clearing jammed guns or adjusting sensitive equipment. Boot designs elevated crew members above the freezing metal floor, using integrated insulation platforms. The aluminum floor of a B-17 at altitude could reach 70 degrees Celsius, cold enough to cause frostbite through standard boot soles in minutes. Officers and enlisted men received identical cold weather gear. There were no special heated stations for pilots or bombardiers. Survival requirements overrode rank distinctions above 20,000 feet. Every man aboard faced the same thermal challenge, and every man received the same technological solution. But maintaining body heat in such conditions required more than equipment. It required systematic operational procedures that managed cold exposure throughout every phase of the mission. B-17 crews followed cold weather operational protocols specifically designed for high-altitude survival, documented in 8th Air Force operational orders. Mission planning documents from Thorpe Abbotts Airfield, home of the 100th Bomb Group, revealed the preparation techniques that made survival possible. Pre-flight warm-up procedures began hours before takeoff. Crews spent 30 minutes in heated ready rooms, bringing core body temperature up before exposure. This wasn't comfort, it was medical necessity. Starting a mission with elevated core temperature provided a thermal buffer against the coming cold. Oxygen pre-breathing protocols required 15 minutes of pure oxygen before takeoff to prevent decompression sickness and improve cold tolerance. The pure oxygen saturated the bloodstream, improving circulation to extremities and reducing the risk of altitude-related complications that compounded cold injury. Scheduled movement requirements were mandatory every 20 minutes. Crew members performed specific exercises at their stations, documented in the gunnery training manual as circulation maintenance. Waist gunners would perform arm circles. Ball turret gunners rotated their feet. Even the bombardier lying prone in the nose performed isometric muscle contractions. These movements prevented the deadly stillness that allowed cold to penetrate even the best insulation. Hot coffee and soup thermos systems provided crucial internal warming. Specially designed vacuum flasks could maintain liquid temperature for 6 to 8 hours. Ground crews filled these containers with near-boiling coffee and soup just before engine start. The thermos system described in the 91st Bomb Group Operations Manual was particularly clever. The containers used double-wall vacuum insulation, technology borrowed from scientific laboratory equipment. Each crew member received 32 ounces of hot liquid that remained drinkable throughout the mission. Sipping hot liquid provided internal core warming that external heating couldn't match. The psychological boost of hot coffee at 30,000 feet over Germany was immeasurable. Coordinated relief protocols allowed crew members to take turns in the slightly warmer radio room. The radio compartment, being more enclosed and containing heat-generating electronic equipment, maintained temperatures 10 to 15 degrees warmer than the open waist gun positions. Rotating exposure to the coldest positions prevented any single crew member from accumulating dangerous cold exposure. Mission rations supplied 3,500 to 4,500 calories through high-fat breakfast, in-flight chocolate bars, and dextrose tablets. These weren't treats, they were essential fuel for cold weather metabolism. The human body burns calories at an accelerated rate in extreme cold, and crews needed concentrated energy sources that could be consumed without removing oxygen masks or heavy gloves. Base operations at Kimbolton Airfield show the industrial scale of cold weather preparation. Heated crew quarters ensured crews started each mission warm. Specialized drying rooms for flight gear, because wet insulation was useless insulation. Medical sections monitoring for early signs of cold injuries, catching frostbite before it became debilitating. The infrastructure supporting each mission was extensive and deliberate. But where did crews recover from the brutal cold exposure of each mission? B-17 crews weren't actually at altitude continuously. Recent archival research has uncovered the extensive ground infrastructure that made repeated high-altitude missions survivable. Recent analysis of 8th Air Force Base layouts by historians at the Air Force Historical Research Agency reveals over 120 air bases across England, each with sophisticated cold weather support infrastructure designed specifically for high-altitude bomber operations. The scale of these operations only became clear with declassified base engineering surveys from 1943-1945. Research at RAF Bassingbourn, home of the 91st Bomb Group, by Cambridge University's History Department revealed what these bases actually provided. Heated barracks maintained at 65 to 70 degrees, ensuring crews could fully warm between missions. Medical facilities with specialized cold injury treatment protocols and staff trained to recognize the early stages of frostbite, trench foot, and hypothermia. Gear drying and maintenance buildings where heated suits were tested and repaired after every mission. The electrical suits took tremendous wear, and maintenance crews spent hours checking connections, replacing damaged wire, and testing rheostat controllers. Industrial laundries processing thousands of wool underlayers weekly because the moisture-wicking base layer had to be clean and dry to function properly. Even heated latrine facilities because crews needed to maintain hydration despite the cold, and cold weather increases urination frequency. On the ground, bomber bases possessed sophisticated heating technology that engineering constraints prevented from transferring to aircraft. Base heating plants burned thousands of tons of coal monthly, generating steam heat distributed through underground pipe networks. Heated ready rooms brought crews up to safe core temperatures before missions, with thermostats maintaining precise 75-degree non-herb temperatures for pre-flight preparation. Post-mission hot showers and hot meals provided rapid rewarming, medical necessities as critical as any other post-flight procedure. Flight surgeons monitored crew members stepping off missions, watching for the telltale signs of cold injury, the pale waxy skin of frostbite, the confusion of mild hypothermia, the stumbling gait of crew members who had stood at their stations for 10 hours in conditions that would kill unprotected humans in minutes. Boeing engineers possessed the technology for cabin heating. Commercial airliners of the era had pressurized heated cabins. The technology existed. They deliberately chose not to adapt it for the B-17 due to combat vulnerability, weight penalties, and fire risk in an oxygen-rich environment. The decision wasn't made lightly, and it wasn't made in ignorance. But why choose individual heating over cabin systems when other nations found different solutions? While American B-17 crews relied on personal heating, German bomber designers had developed rudimentary cabin heating systems by 1942. The Heinkel He-177 included a gasoline-fired cabin heater that used exhaust heat to warm the cockpit area. Japanese bombers like the G4M featured charcoal heating systems, traditional technology adapted for aviation. British Lancaster bombers used a similar philosophy to the B-17. Electrically heated suits with no cabin heating, documented in RAF technical manuals and Bomber Command operational orders. Soviet P-8 heavy bombers included cabin heating but flew at much lower altitudes, typically 15,000 to 20,000 feet, where the system was practical and the fire risk manageable. German late-war jets like the Me-262 used engine bleed air for cockpit heating, but this technology wasn't available for piston engine bombers. The turbojet engines produced abundant hot compressed air as a byproduct. Piston engines didn't generate this convenient heat source. Americans weren't unique among Western allies in rejecting cabin heating. RAF Bomber Command analysis shows nearly identical patterns: personal electrical heating, layered insulation, and operational procedures rather than aircraft-wide environmental control. The British arrived at the same conclusions through independent engineering analysis and operational experience. German and Japanese heating systems proved unreliable in combat. Multiple Luftwaffe loss reports cite cabin heater fires as contributing factors in aircraft losses. The weight penalty reduced bomb load by 400–600 pounds. Combat damage to heating systems proved more dangerous than simple cold exposure. A punctured heating system could flood the cabin with carbon monoxide, toxic fumes, or superheated air, all immediately incapacitating. Boeing made a calculated trade-off. Eliminating cabin heating saved 400 to 600 pounds of equipment weight, allowing an additional 2x 500-pound bombs per mission. It eliminated fire vulnerability in oxygen-rich environments, where even a small flame could become catastrophic. It proved more survivable when battle damage occurred, because there was no centralized system to fail, only individual heated suits that could be disconnected if damaged. These were critical advantages for daylight strategic bombing, where B-17s flew into the most heavily defended airspace in history. Could crews actually survive these conditions, or were cold casualties devastating? Historical medical records from the Army Air Forces confirm the personal heating strategy worked remarkably well. Analysis of 8th Air Force medical reports from 1943 to 1945 by the Air Force Historical Research Agency shows that of over 350,000 combat sorties flown by B-17 crews, cold-related injuries accounted for less than 3% of medical evacuations. The vast majority of frostbite cases occurred when electrical heating systems failed due to battle damage, or when crews removed gloves to clear jammed guns. Operational failures, not system design failures. Electrically heated suits maintained core body temperature effectively in over 90% of missions. Layered insulation provided adequate backup when power systems failed, with properly dressed crew members surviving electrical failures that would have been immediately fatal with cabin heating dependency. Operational procedures minimized cold exposure duration and severity through systematic warming breaks and coordinated position rotations. Ground infrastructure enabled recovery between missions, preventing the cumulative cold injuries that would have grounded crews after repeated exposure. But the survival statistics revealed something unexpected. The psychological toll of cold missions proved as significant as the physical challenge. Combat crew questionnaires from over 2,000 airmen studied by military psychiatrists in 1944 show that fear of cold injury ranked third among crew anxieties, behind fear of being shot down and fear of fire. Post-mission debriefs consistently mentioned cold as a major stress factor, affecting crew performance and decision-making. Crews developed informal support strategies to combat this psychological burden. Buddy checks for frostbite symptoms became standard practice, with crew members monitoring each other's faces for the white patches indicating frozen tissue. Shared thermos rations created moments of connection at altitude, encouraging cold crew members to keep moving, to stay active, to fight the deadly lethargy that extreme cold induces. Squadron commanders recognized that maintaining morale required acknowledging the cold challenge rather than dismissing it. Official recognition that flying at 60 degrees for 10 hours was genuinely difficult, genuinely dangerous, helped crews process the experience and prepare mentally for the next mission. The cold wasn't denied, it was managed. B-17 crews conquered the stratosphere not despite their lack of cabin heating, but because of Boeing's decision to reject it entirely. Technical documentation from Army Air Force's engineering, archives and medical records from 12 major bomb groups definitively establishes that B-17 flying fortresses operated without cabin heating systems throughout World War II. This wasn't wartime, shortage, or rushed engineering, but calculated aerospace design philosophy. Boeing engineers prioritized mission capability and crew survivability over individual comfort. Their remarkable success stemmed from revolutionary personal electrical heating technology that provided warmth without aircraft-wide systems, sophisticated layered insulation that functioned even with power failure, systematic operational procedures managing cold exposure through mission planning, extensive ground infrastructure enabling recovery between missions, and comprehensive training preparing crews for high-altitude environmental challenges. Rather than frozen warriors enduring constant suffering, B-17 crews were the beneficiaries of revolutionary aerospace engineering that solved the high-altitude cold problem through distributed personal systems rather than vulnerable centralized heating. They balanced mission performance, combat survivability, and crew welfare through innovative technology and systematic procedures, not through brute endurance. B-17 crews flew over 290,000 combat sorties from England. They delivered 640,000 tons of bombs on strategic targets across Nazi-occupied Europe. They maintained operational capability in conditions that would ground modern aircraft. They achieved it all in unpressurized aircraft at 30,000 feet, deliberately flying without cabin heating. When your car's heater fails on a winter morning, when you instinctively reach for the thermostat when you feel a chill, remember that B-17 crews made the conscious decision to fly without such comfort. Every single mission, they chose combat effectiveness over personal warmth, distributed systems over centralized comfort, mission capability over individual ease, strategic success over tactical convenience. Point crews didn't just endure the cold, they systematically engineered personal solutions for it. They restructured aerospace design philosophy around it. They reimagined what was survivable at 30,000 feet. In the end, B-17 crews didn't need cabin heating because Boeing engineers had learned something far more powerful: how to keep individual humans alive through distributed personal systems, innovative technology, and strategic engineering, rather than trying to heat the unheatable sky. And in that transformation from comfort-dependent earthbound thinking to cold-adapted high-altitude aerospace engineering, they became the crews that could strike targets no other force could reach, flying higher, longer, and more effectively than anyone thought possible. They became the men who won the air war over Europe, one freezing mission at a time,